Hello everyone, welcome you all to Technobiz Rubber Tech Talk. Sorry, Namaskar. This is a virtual event series for the rubber, latex, and tire industries that we organize on regular basis. We invite experts, specialists related to the rubber, latex, and tire industries to share their experience and knowledge to the global rubber community. And today's episode of the Technobiz Rubber Tech Talk, we're focusing on the very interesting and important subject on the rubber materials for electronics application. Our invited guest speaker is Dr. Titash Mondal. He is an assistant professor, Rubber Technology Center at IIT Kharagpur, Indian Institute of Technology Kharagpur. He is one of the well-respected, recently received an award from the ACS Rubber Division as well. Very innovative researcher, always interested to develop new things for the benefit of the industry and new applications. Today is going to give a talk on the rubber materials for electronics application. Please join me to welcome Dr. Titash. If you have any questions on this presentation, you can post questions in the question box and we address questions at the end of the presentation. And let's invite Dr. Titash to give a talk.
Thank you, Peram, for the invitation. I'm really happy to share my views and the findings, whatever my research team has been recently doing on this particular rubber-based materials for electronic applications. So for the next 1 hour, I'm going to talk about the same. So like Peram introduced, I am working as an assistant professor in the Rubber Technology Center, which is very unique in India as well as the world, because since its inception in 1981, this center has produced many stalwarts who are currently serving in the rubber fraternity, both in industry and academia. And those who have not been to IIT Kharagpur, this is like our wonderful campus. It's a huge campus. Green campus, as you can see here. Just let me switch on the pointer. This is something which is the main academic building, and this is a kind of an aerial view of our campus. As you can see, it's a very green campus. And this is from where IIT Kharagpur, being the mother of all IIT, started long before. So and in addition to that, I would like to present a disclaimer that the views, whatever I am presenting here, is just based on the understanding of mine and my research scholar, and IIT Kharagpur does not endorse it in any form. Okay, so having said that, let me begin today's talk, which is basically on the rubber materials for electronic applications, because holistically, if we see rubber materials, whenever we talk about any rubber materials, the first thing that comes to our mind is basically products like tires, seals, gaskets, okay, and also adhesive in some or the other form. These are the traditional materials that come to our mind when we discuss about the rubbery materials. So, but what we are trying to, or rather what my research team is trying to do currently here at IIT Kharagpur is to start a new domain or try the application of the rubbery material into a new type of or new generation of material by leveraging the learning what we do for the traditional material. So what we are doing something, or we are doing the compounding which are being regularly done in many places, but what we are doing certain minor tweaking and giving it a new application. And my research team's application is mostly focused on electronic space. So next 1 hour, what we are going to do is talk about the different developments that we are doing. Now, in most of the electronic applications that we are currently focusing on is based on rubber nanocomposites. So before even we go into the actual topic of the rubber materials for electronic application, let us try to understand what exactly is a rubber nanocomposite is, or what exactly, how does, or what is the world of nanomaterial is. Like for that, as you can see, On your left hand side, there is a scale bar, which you can see here. It's just a scale, which is depicting the size of different commonly seen material around us. Like for instance, if we take a height of a child, it can be something around 1 meter or 10 to the power 0 meter. We can refer to that. Okay. Now, when we see a ant, okay, or a fly, typically, these are typically of the range of 1 millimeter or 10 to the power minus 3 meter. Now, if we consider a human hair, this is something which is basically around 10 to the power minus 4 meter. Okay. And then when we are going even down, like the DNA, which is considered to be as the basic building block of any human being, there those DNA elements are something which are of the order of 10 to the power minus 9 meter. And this 10 to the power minus 9 meter is nothing but 1 nanometer. So when we take a material of such size and shape, which is having either their lateral dimension or their thickness or size in that particular nano range actually, or to be very precise, below 100 nanometer, we can effectively call those materials as a real nanomaterial. Okay. Now, when you take that, nanomaterials, basically, they are in most of the cases are very light, okay, very low dense material. Like for instance, if you see, this is a kind of a page or kind of a image which I got from the General Electric's website. So basically what they are telling, if you are taking 1 gram of graphene, I'll come in the next few slides what exactly a graphene is. If you take 1 gram of graphene, what you can do is basically cover an entire soccer field of this particular dimension. So now you can understand that this nanomaterial, how less is the density of the material. So it can have a wide coverage of a soccer field of this particular dimension. Okay, and this makes it very much different from the traditional microfillers like carbon black or any other material. Now, this nanomaterials, due to their unique shape and size, does demonstrate unique properties like their strength, okay, their barrier property, their electrical property, their electronic properties are quite different than the traditional macrofillers actually. So that's what brings in the novelty to the composition when you mix this nano material into any polymer. So that means at a very low dosage, actually, you can achieve good performance compared to the macro composite in which you are putting those big size fillers and achieving the properties. Now, this nanotechnology, if you honestly say, this is not something very new. Actually, I say that every kid, even my 6-year son, is also a nanotechnologist. You must be wondering, why am I telling that? Because on the extreme right hand side, what you are seeing here is a scanning electron micrograph image of a pencil. Actually, the tip of a pencil, which is nothing but a graphite. Like whatever we see, this tip of a pencil, that is under the microscope looks like that particular shape. Now, do you know why does, when we write with a pencil, why does it mark the paper? The reason is basically this material, which is essentially a graphite, is a 3-dimensional material. It is more like stacks in this particular fashion. Like, if you follow my hand, you can see there are multiple such pages are kept over here. Okay, and this, this forms a 3-dimensional structure. But in the case when we are writing with a pencil, what happens is that one single layer is typically sliding off from this whenever we are putting a pressure on the paper, and that's why it is creating a mark on the paper on which we are writing. So this particular single layer or few layers that are basically slipping out of the tip of your pencil is a nanomaterial, because the three-dimensional graphite, as per the International Union of Pure and Applied Chemistry nomenclature system, that is something not a nanomaterial. But whenever the number of layers is less than 9, any number which is starting from 1 to 8, such layers, if you talk about, that materials becomes a nanomaterial. So that's why I call every child who writes in the school or who just begins to write in the school is equally a nanotechnologist. So you can see there is an immense contribution of nanotechnology right at the beginning of your career. Okay. Now, what exactly is a nanocomposite then? This was something about a very brief background about the nanomaterials which are commonly encountered in our day-to-day life actually. Now, when should I say a material is nanocomposite, or rather rubber nanocomposites or polymer nanocomposites? So basically polymer material or the rubber that we take, in that if we put this nanomaterial basically, so it becomes a nanocomposite. Or in other way, we can say that whenever a rubber material or a rubber composite is having a filler which is having at least one of its dimension in nano level, can be referred to as the rubber nanocomposites. So like that way, if you see, this particular nanocomposites finds multiple applications in different areas. Like for instance, if you look into the tires, they are doped with the nanomaterials, nanofillers like graphene, carbon nanotubes. This type of materials are equally used along the side of the traditional carbon black or silica to improve the properties of the tire. Similar is the case for the, like, shoe soles. Actually, there are a lot of companies which are coming up with the incorporation of graphene in the shoe sole, specifically for the shoes which are utilized in areas like hiking. Okay, so you can see that this material, these nanomaterials are being incorporated into the rubbers for different industries, which are basically ranging from defense to the energy storage. You can see there is a whole lot of thing. But what is interesting nowadays is basically the concept of electronics. Because why do we say that? In the case today, we are living in a smart world. Actually, everything is connected, everything is internet connected. Just with a tap of thing, you can get whole list of information. So in this era of connected world, there is a huge role which is played by the sensors which are typically used. Okay, now what we decided is that let us take a look into the different possibilities of utilizing this rubberized material for sensing applications. So I'm going to talk about 2-3 such case studies where this rubberized nanocomposite based sensor can play a critical role in determining different properties. Using those sensors, you can get some idea. And as you can see from this particular slide, actually here, you can see that this rubberized sensor, if you see, they can in fact find application in human health monitoring, human machine interface, smart health monitoring, and the smart agriculture sector. So in a nutshell, you can see this type of materials finds a lot of applications using this type of rubberized sensor. Okay. Now, when I talk about this rubberized sensors, okay, we have to understand a few fundamental involved in this particular, system. What exactly is the rubberized sensors, and what are the typical strategies typically utilized for making this, sensor element? Okay. Now, rubbers, honestly speaking, does not have a very strong role in the sensing mechanism, because rubbers are typically electrically insulative in nature. And when we talk about the sensors, basically they are either like, pressure sensitive or capacitive or electrically resistive type of sensors. Okay. Now, to have this particular rubber, which is electrically insulative with nature, to make it an sensing material, what we need to do is basically formulate the rubber and make it electrically conductive in nature. Okay. Now, for that purpose, what we do is basically we take different nanomaterials, or I should say electrically conductive fillers. And why we need a nanomaterials? Because like I said in my previous slide, that we can achieve this property at a very little bit of amount of addition of this nanomaterial into that and get a kind of a formulation ready. We can achieve the same with carbon black also, but in that case you need to load a lot of carbon black into the formulation. Now, the typical nanomaterials what we take here ranges from multi-walled carbon nanotubes. It can be graphene. It can be hybrid of carbon nanotubes and the graphene. And then there is a new class of ceramic material which is known as the M-zenes are also being taken and added into the rubber. So the rubber brings in the flexibility and the nanomaterial brings in the electrical conductivity into the system. Okay. Now what happens, like, we can load, like for instance, if we are looking into the traditional rubber formulation, the basic question is that what PHR or what loading of the particular nanomaterial should I do in this particular rubber to make it behave as a sensor or electrically conductive in nature. To understand that, we have to see a fundamental physics here. Now, what is that particular physics? Like here in this particular GIF image, you can see that this is at a very low filler loading actually. So what happens is that when you are just adding the filler into this nanomaterials into the rubber, they kind of remain in a scattered way. They are not interconnected like this way, what you can see here. But if you keep on adding, actually what it does, it starts forming certain network structure, and it goes and it saturates at one point actually. So this network structure is something known as the percolative network inside the rubber matrix. So in other way, if this is something, a kind of a block of rubber which is having a kind of a filler in it, so what happens is that if I source a current from one terminal and if I measure the current at the other terminal, what will happen is that it will pass the electricity through it, or the electrons can basically pass through this whole matrix. Okay, and then that is possible due to this network structure of the fillers which are typically forming here. And how do we monitor that? We monitor using the measurement of the electrical conductivity or the resistivity of the sample that we are making. For instance, there are three definitive zones actually, and this is from the electrical percolation theory. On your y-axis, basically, you can see the sigma AC or DC corresponds to the electrical conductivity of the system. Okay, and this is VF corresponds to the volume fraction. Now, in place of volume fraction, we can use weight percentage or we can use the PHR as well. So initially, when we are putting the fillers over there, as you can see, they remain in a very discrete structure. They are not connected to each other. But after a particular loading of the filler, what happens is that each individual fillers starts to get contacted or establishing contact with each other. Okay. Now this is what is known as the percolation point. Okay, that means electrons can percolate just at this particular point. And from this, let's say, so what you get to see here is that there is a potential increase in the conductivity, or there is a sudden jump in the electrical conductivity of the rubber composite that you are working on actually, and thereby you can say at this particular concentration, if you drop down a line here in this x-axis, you can get an idea at what volume fraction or what PHR of filler you are establishing the first, percolation network structure which is forming over here. And then if you keep on increasing, what happens? It goes on increasing to a particular range, and then it saturates, almost it plateaus down actually, showing that all the networks are saturated, no further new network formation is possible now, and the material's conductivity has reached almost a saturation. Now, for technologists like us who are working in the domain of sensors, we are really interested in this critical volume fraction of filler where the first percolation network is established. Why do I say that? Because we measure the sensor's response with respect to a term known as the relative resistance change, relative resistance of the electrical conductivity, whatever electrical resistance change. So that's what you can see here, R by R0. Now this R0 is something which corresponds to the initial resistance. That means at this particular point, when there is no disturbance to the sample, there is no pressure, there is no strain, there is no temperature acting on the sample, it is kept under ambient condition in an undisturbed situation and under no influence of external stimuli, the electrical resistance that you get here is normally referred to as the R0. Now let's say you are disturbing the material, like you are typically stretching the material in this particular way. Okay. Now if you are doing so, what happens is that this network structures, whatever is established, are also going to break parallelly, because if you are pulling the rubber sample like this, you are disturbing this network structure which is under static condition. But when you are pulling it, basically there is a change in the particular network formation over here. They will get disconnected from each other, and if they are disconnected from each other, what will happen is that there will be an increase in the resistance. That means the sample will be less conducting because the electrons cannot flow through it appropriately. So what you are going to get is a delta R factor. Now this delta R is resistance at time t under the influence of any external stimuli minus the resistance R0, which is measured under undisturbed condition. So this is what gives you the relative resistance value, or the delta R by R0 value. That gives you an idea about how much disturbance is created over here. And this is how mostly the resistive type rubber sensors typically work. So what people do is that they kind of either strain it and check the relative resistance value, okay? And if the change in the relative resistance value is very high, that indicates that the sample is extremely sensitive, okay? Now, if the value delta R by R0 is small, that means that it cannot show much changes. So we are playing around this sensitive region, and that's what brings in the sensitivity of the rubberized sensors that you are making. Higher the delta R by R0 value indicates higher sensitivity of the sensors that you are doing. Okay, and I'm not going into the details. Basically, this particular sensitivity, if you see, like this is something as a strain. You can understand that we are pulling the sample, there is a dislocation happening between the network structure, but there are other factors also, like if you are increasing the temperature or decreasing the temperature, the electron transmission through this network structure is also affected, because in some of the cases with an increase in the temperature, the polymer structures, the chains, whatever is present in the bulk, also kind of flows to a certain extent, or there is a certain volume expansion that happens, and those type of things pushes this effective electron connecting bridges actually, and disturbs the electrical resistance of the material. So you can understand that if you are able to make a very sensitive material, okay, factors like strain, pressure, temperature, you can develop different classes of this type of sensors. Okay. Now, in terms of the fillers that you are selecting, from our experience, we have seen that if you are taking graphene as the conductive fillers, they are very good for temperature sensors. Whereas if you are taking carbon nanotubes as the particular filler, actually, you get a very good strain sensors, and you can create these sensors at an ultimate low loading of carbon nanotubes, like something around 0.05 volume fraction, okay, or 0.05 weight percentage also in the rubber. You can get very good sensors developed, but that also depends on what type of rubbers you are taking, or what is the molecular weight of the polymer that you are taking, because it is all connected through the radius of gyration of the materials, and other factors are also involved. I'm not going into the details about the same. So this is how typically the sensitivity of the materials or the sensors that we are making is determined. Now, coming to the manufacturing of this material, what we call is, typically when we say sensors, we think of very robust manufacturing facility, very high scale, high end facilities and instrumentation facilities. But what we are doing in a clean room free facility. Typically sensors are manufactured in clean room, where you have ambient temperature, humidity, and it's a dust free environment. But all we know, rubber industry, you cannot afford to have all these facilities all the time. So what we do is leverage the traditional techniques like compression molding, okay, to make this kind of sensors. Okay, in fact, injection molding can be also leveraged for making this type of sensors. In addition to that, what we are also doing is something which is very unique. We call it as a printing technique. Like, for instance, you might have seen that there is a material known as plastisoles, which are commonly used for printing different patterns on t-shirt. So what they do is that they have the green color material, which you get to see here, is typically referred to as the mask. Okay, and here you have a typical design. Let's say if I have a t-shirt like "I love Technobiz," okay, or "Thank you Peram," like that, okay, I have a design of similar sort. What I need to have is a basically ink, and that ink I need to put it, and then there is a squeegee at a particular angle and a pressure. You need to pull it down, and whatever mask design you are having here, that will be getting printed on the substrate on which you want to make this type of thing. So we kind of took that idea, and we started working on the screen printable sensors also, where we can make different fine designs on the mask, and we create a functional ink with rubbers. Now this rubbers can be a liquid rubbers, okay, or it can be even the solid rubbers dissolved in a particular solvent. But in most of the cases, when we are taking the solid rubbers and dissolving in solvent, the solvent comes into the picture, and that is sometimes environmentally not so benign. So what we have established, this particular technology, is using a liquid rubber. So this is another neat way using which you can make this particular rubberized sensors. Now the other one is even more simpler. It's like, I saw my son using a stencil for writing A, B, C, D, and things like that, star shapes and all those kind of things. You are dumping some, colors on that, and getting those impression of the stencil. So I thought that it could be very well translated into this sensor also, because anyhow, we are making this rubberized inks. We can just take it, put it into the stencil and print it. So what we can come up is basically stencil printable sensors. And this stencil printable sensors and the screen printable sensors are very thin in nature. It can be printed on textiles, It can be printed on any substrate of your choice. But there is a caveat. You need to have a good rheological property of this particular ink, because not all the inks that you do can stabilize, or there you can see also a phase separation between the nanomaterials and the matrix. So what you need to have is a good coherence between the fillers. You need to add those specific additives so that even after printing, the material remains in a good shape and condition. Otherwise, rheologically, if the inks are not optimized, even though you are printing it, you might see other adverse effect and you might not get good functional attributes of the sensors. Okay. So with this basic, actually, this basic is very much needed before I go into more complex things actually. Now, I'm going to show you two such case studies wherein we have used this rubberized sensors for healthcare monitoring. Now, if you see India and many other continents, India is in a still better shape, I would say. There are many African nations also which does not have appropriate healthcare facility in remote places. We call this as an extreme condition. Okay. Now, what we can do is basically utilize this type of printed sensors, or this sensors developed using compression molding for use as a class of material which is known as point of care devices. Now, point of care device is something which is very simple in nature. Like anyone having a blood sugar and knowing an instrument known as glucometer, using which you can check your blood sugar sitting at home, is also a point of care device. So in that case, what you need to do, you have a lancet, you just need to prick in, and the blood that is going to come out, you need to take it on a kind of a paper-based strip, and that strip is connected to a device, and that device typically gives you the blood sugar level. So just at sitting in home, you get an idea about what is your sugar profile, and this is something known as the point of care devices. Now, I was talking about the austere environment, or the environment where you do not have good medical facilities. What you can do is basically, if you can develop such kind of sensors which provides this immense physiological information for you, okay, just at sitting home, that could be wonderful. So what we targeted is two particular disease and problem which is very much pertinent across the globe. So the first one is something which is known as the chronic obstructive pulmonary disorder, or what we know is basically COPD. Now, if you see, this is something which I got from the internet. Like COPD is something, a problem happening throughout the world. I mean, thanks to the increase in the pollution and many other factors, secondary factors, what you get to see is that there are a lot of COPD patients. Okay. Now, in the case of the COPD, what happens is that your sacs, like, your lungs, whatever you are having, they do not deflate like a normal lung. So as a result of which, what you get is problems like breathing disorder and all those kind of things. Okay. You have a lot of problems. So what we thought is that, can we make certain materials which are typically can be leveraged for developing a smart mask. When I say a smart mask, it is nothing but a typically N95 mask. Now again, COVID is back in many places. What we see, there is an increase in the usage of masks, and you might have seen that there are certain masks which comes with a filter. Okay. So what we did is that we very smartly removed the filter from the mask, and what we replaced it with is something, as you can see in the camera, a very small patch like this. This is a printed sensor on a PET substrate. Okay. And then what we did is that we affixed this particular thing on the mask. In the next page, I will show you the image. And this work was done by one of my students, Dr. Simran Sharma. So what she did is that she developed this particular mask. As you can see here, this is the mask, and here this particular sensor which I was showing here is particularly attached here. Now this particular sensor is very sensitive. Sensitive in the sense like this is something which works as a strain sensor. Now you need to understand there are, when you breathe in, breathe out basically, and when you are wearing a mask, what happens is that you are generating air pressure over there, and then there is slightest disturbance. So this mask is something, this sensor, due to the exhalation of the air inside the mask, is going to move little bit, okay? And this sensor is so sensitive, it can very accurately pick up those particular information from this, how much is the movement happening per second, okay? And if you can do that, basically, what you get to do is you can connect it very well with the breathing pattern. Like for instance, if you see normal human being, the breathing rate is around 16 to 20. Okay. What we did is that we picked up this particular mask, we used it, and what we see here is if you do the peak counting, actually, this is for a normal breathing, you get like, in 60 seconds around 18 peaks actually. So that indicates that the person is having no problem in the lungs. But if a COPD patient is wearing this, okay, or a patient which is at the onset of COPD, immediately what you are going to get is an indication in this normal breathing pattern. That means the number of peaks that is supposed to come due to the movement of this particular material, okay, is going to be lower in number. And at the end, what we are measuring is again the relative resistance change. But where we are connecting it to the normal breathing pattern, okay? And similarly, it can work. You can see that this material is something can be also checked for the fast breathing pattern. In fact, see, this is a classical case where we intentionally didn't breathe at all. We hold our breath. You don't see any peak because there is no movement of this particular sensor happening due to the exhalation of the air. So what you get is a flat line over here. Okay, like this way, we developed a very nice mask material. In fact, this work was highlighted by the Nature Group also, Nature Publishing House, as a unique invention. Okay. Now coming to the materials perspective, what we did is that we have taken graphene as the filler and we have taken liquid isoprene rubber. Now why we have taken liquid isoprene rubber, I will also come shortly to this one. And we have taken as a kind of a planetary centrifugal mixing technique to make this particular ink. And like I mentioned, using a stencil printing technique, we established this sensor and we attached it to the mask. Now, why we have taken this liquid isoprene rubber? Because you have to, have an advantage of the rubber too. Although I have said that rubber doesn't have much role to play in this sensor, apart from delivering the flexibility, but sometimes, you have to trick the rubber also. Because coming to the application perspective, there are a lot of armed forces who are sitting in very high altitude area. Like in India, if you see, our defense forces are also in Siachen and places where the temperature is extremely low, like around minus 40 degrees C around the year. Okay, so typically they also have this type of problem, breathing issues and all those kind of things. But unfortunately, all the sensors which are commercially available, they have a very limited functionality at low temperature. They cannot play very well at the low temperature. Okay. What we decided is that when we are taking this liquid isoprene based rubber, and if you look into the glass transition temperature of this material, it is roughly around minus 65 degrees C. So which is well above the operational condition. Okay, well below the operational condition. So we have tested this material even function, and this type of respiratory patterns can also be captured even at a low temperature of minus 40. So that makes this unique combination of the rubber and the graphene for making this particular kind of point of care devices. Okay. Not only that, What I'll do is that I'll also switch on the video. As you can see here, these are all IoT connected. Actually, we did a kind of a smaller variant of this. Like you can see, bulky breadboards and all those things. We changed everything. Okay, and these are all IoT connected. That means whatever you are doing, you can get the output of the result in your mobile phone as well as laptop. Not only that, what we also did in this particular case is something you can calculate the peak height and the peak area, and from there you can get many vital informations like something known as the T in and T out. This is something which is also deeply related to your lungs profile. So we consulted the doctors also, and whatever value we got using this mask is very much within the limit. Okay, so this is something very unique development. You can see just by utilizing a rubber based sensor, you can develop this smart mask, and which can be very well, sold under the point of care device category. So this is one of the classical example I thought of sharing. Now coming to the next one, which is again a kind of a burning problem across the globe, which is known as the cardiovascular diseases. If you look into the percentage of the people affected globally, you can see there are around roughly 20.5 million deaths everywhere. Around 33% of all global deaths that's happening, cardiovascular disease is the root cause for them. Okay, so you can see this is something from the World Heart Federation. Okay, now one of the primary reason for this cardiovascular disease, there could be multiple factors which is involved here, but one of the primary reason for this is something known as the atherosclerosis, which is nothing but a plaque deposition into your arteries. Just like we use the pipes for drainage of water, sometimes we see if there is any kind of deposition of material happening, the water will not pass effectively, and if it doesn't passes at all, at the end it bursts off, or it kind of loses from the joints actually because of the building pressure over there. So similarly, our arteries that which are present over here in our human body are also like pipes, and due to our lifestyle, due to our eating habits and things like that, what you get to see is that there are a lot of plaque deposition happening for many people if you are not maintaining a healthy lifestyle. So what happens in those particular cases is that in those cases, your arteries normally loses its elasticity, okay, and it becomes more stiffer. So then what happens is that when you are basically the blood is flowing through this, it is going to generate a lot of pressure into the system, and due to loosening of this elasticity, the arteries are also going to show a lot of stiffening behavior. Okay, we did this study, and what we thought is that we can provide a solution using a rubberized sensor which is strain sensitive, but still it can give you an idea how is your pulse is, like if there is any abnormality in the pulse, whether any arterial stiffness is happening or not, we can get all those information. Now there are some solutions which are available in market, which is like this particular current product, if you see, using the tonometry technique, and if you look into the ballpark costing, I don't know if any international audience is there today, but this is, I have quoted in Indian rupees actually. Roughly for euro you can just divide this number with 90, or for pounds you can divide this with 100. So these are expensive material. The current technological solutions which are existing are very expensive, but what we thought is that if we can have a rubberized sensor which is sensitive, providing very good solution, okay, and information without losing the sensitivity, nothing better than that. Okay, and this is going to be something contribution towards the affordable healthcare, which is also the need of the hour. So with that thought process, what we did is that this is my student Mutamil, who started working on the development of this type of printed sensors. And the sensors is again something like this. What you can do is basically place this sensor in your radial artery position. In this particular position, you can place it, and then what you get is very critical information about your pulse rate. So I'm going to come in details, and by the time what I can do is also I can also show you this particular video which can play at the same time. But just give me a second. Uh, yeah. So at the same time, you can see this video parallelly happening at the back side actually. So here, this particular sensor is attached, and on the screen, what you get to see is the human pulse, which is being recorded over there. Now, why this material is recording the human pulse? The reason is basically when the blood flows through your artery, it introduces certain strain on the screen, and the strain level is something around 0.25%. Okay, so you need to have a sensor which can even sense that high, I mean low number of strain actually, I mean that low percentage of strain. So it has to be very sensitive material. Okay, and accordingly what we did is that we made this particular sensor which can very nicely detect that strain, and this relative resistance change, as you can see at the bottom of the page actually, this is something which is giving you the pulse beat. And if you see, this was done on healthy individual, and you get to see is that this is having a 68 beats per minute. In fact, currently the Indian Council of Medical Research has funded me a big project to carry out this material development. Okay, and this is something what you get is the bending strain actually over multiple cycle, and you get to see that there is no electrical hysteresis happening over there, showing the effectivity of the material over multiple cycles actually. Now coming to the arterial stiffness part actually, what you can do, you get to see here, this is something, a peak which is captured from one of the peaks which are shown here. So you get to see here there are three parts of this particular peak, as you can see here. One is the top part, then this is P1, this is P2, this is P3 actually. Okay, so what you can do is basically measure the height of the peak. We made an algorithm which can automatically measure the height of the peak for every individual, and the time taken from this peak to this peak, right? This is a time scale what you get to see here. We made an algorithm for that, and using this basically what you get several information about the individual's heart condition, whether the person is something at the onset of any particular cardiovascular disease or not, because in many cases whose cardiovascular disease starts with this arterial stiffening, what they face is that initial disease the artery becomes very stiffer, and from this particular case we can do certain, through algorithm fitting you can do something, a point care map for heart rate variability. Okay, and from this particular matrix actually you can get an idea is that whether an individual is at the onset of the cardiovascular disease or not. We call it as early prognosis for the cardiovascular diseases using this type of rubberized sensor. Now the good part in both the cases is that you have to see, in the first case the sensor was attached to a mask. It is not in direct contact with the individual. And in the second case also, the sensor is at the top and it is through the PET, it is attached to the skin. So in none of the cases, even though this is a healthcare material, the sensor, rubberized nanocomposite, whatever we are developing, is not in direct contact with the human. So you do not need to take really the permission or the clearances for this material, because this is in a non-contact mode. Basically, you are getting all these informations. So with this, we were doing pretty good. We made a lot of type of, if you see, like beautiful sensors for different types, like motion monitoring, okay, temperature sensors, all type of things. Like you see, two of our works got highlighted in Nature. Okay, we were doing very nice in terms of the research, actually, in terms of the sensors. But the problem with this sensors are that these are all battery powered. That means you need a material or to make this sensor work, you need an external battery powered console. Now, incorporation of the battery sometimes becomes very tricky, and it possesses formidable challenges in terms of the form factor of the material. So what we decided is that if we can leverage a technology which can help us get rid of the battery, how about that for charging this sensor or powering this sensor? So we call this next generation rubbery materials, which are known as the self-powered material. Okay, that means you do not need a battery to power this material. So we, by creating certain devices due to the electronic condition of this rubberized material, okay, it generates certain voltages, it generates certain power output which can drive the sensor by its own. So it's a unique invention. You do not need any external power sources to generate this or run these sensors. So that brings us to a concept of energy harvesters. Okay, that means you are taking this material and we call it as the triboelectric nano generators. It's like generator that used to be used at one point of time. Now these are nano generator. Basically they are creating the power by its own. You do not need, as you can see, if I click on this particular video, you get to see here, just by tapping, around 500 LEDs can be lit up, and you are not using any battery power. Okay, and similarly here you can see also, just by tapping it, you can power up small, like you can charge up the capacitors, and those capacitors can be utilized for powering up small wearable devices. Like if you see, if you are connecting this to a kind of a wearable device, you see this is getting something powered up. As you will be able to see it very shortly. So you are not using any battery or anything, but you are powering up this material. Now, how is this happening actually? This is happening through the concept of triboelectric nanogenerator. So what is triboelectric nanogenerator? Basically, you have two polymeric materials which are having different electronic properties actually. So that means, like in some of the cases, the polymers can have electron donating group, it can have electron withdrawing group. Now, when you take this material of different electronic properties and they touch each other, so what happens is that transiently there is a charge transfer happening from the donating to the withdrawing part and vice versa, like this way. So this is something, it's like coming in contact and then going back, again coming in contact and then going back, like this particular way. You are basically forcing the electrons to come from one surface to other surface, and then you have the electronics through which you can capture those electrons, and basically by that way you can generate this kind of self-powered material. Now for this particular case, what we have done is we have taken a sustainable material which is natural rubber, and we have modified this natural rubber with a material known as tannic acid, which is again a very green source commonly available in the tea. Okay, so we modified the natural rubber with tannic acid, and then we have taken on the opposite side Teflon as the other pair. And when this particular contact separation between the tannic acid modified natural rubber and the particular Teflon is coming, okay, so I'm sorry, in this particular case we have taken epoxidized natural rubber and then we modified it with tannic acid. When they are coming in contact with each other, they are generating a lot of electrons, and you can see is that it is generating a mammoth power density, like which is around close to 37 watts per meter square. So every meter square of this material is going to generate around 37 watts. So it's a phenomenal material for generating self-powered materials. Okay. Now coming to the next part, actually, we have taken extended this concept to another thing, which is the textile, because we know about a lot of rubberized. Let the video be played at the backside, actually. So in this particular case, what we have done is that we have taken the rubberized textile, and but the beauty of this rubberized textile is that it is a kind of a vitrymeric structure. That means if you are damaging the coating of the rubber on the top of the textile, and if you are showing a heat gun to that, what will happen is that it is going to heal by its nature. It behaves more like a vitrimer. Okay. And for that purpose, what we have taken ENR 50 again as the kind of a material. And then what we did is that we have taken reduced graphene oxide over there, and we chemically modified. So here citric acid was used as a kind of a cross-linker for ENR 50 as well as the reduced graphene oxide. And then we treated with typical, cellulosic textile using a dip coating technique, and we got this rubberized fabrics, which are also energy harvesting in nature, as you have already seen in this particular video. And here also you can see this is something, are excellent touch sensors. You can see in the screen, they are kind of, picking up the signals very nicely if you are touching them. So rubberized textile based touch sensors, okay, can be manufactured using this particular technology. Okay, and at the top of that, due to the dynamic covalent cross linking that is present over here, this material is something which is also vitrymeric in nature. Now, this is again a very freshly baked, I would say. Not only that, we have developed certain smart lock system, as you can see here. So here you have a panel, and these are the kind of self-powered material. You do not need any energy harvester. And this is, if I go back a little bit, here is a lock. So if you put that pattern, you see this is unlocking is happening. Okay. So if you are putting anyone's, and you will also get a kind of an email generated, okay, immediately who accessed this particular system. Now, if you are doing the pattern for 3 or 4 times, 3 times strong, you will immediately also get an email that somebody is trying to breach into the system and break in the lock. Okay, so this is how you can make smart lock systems. So you will see that it is like, for instance, my name is written over here, and this is access has been granted. And if I go a little further, you will see here access is denied this thing, and you also get a kind of an email shooted out to you that somebody was trying to access your home or anything. Now coming to the methodology, what we have seen, like you will see that here that access denied, and this was the tapping pattern that was tried, and this is something which is somebody was trying to break into the system. What we did is that in this particular case, we have used the waste PET bottles, like the one which is there in my office. As you can see, the typical water bottle. All over the campus, we collected all the waste bottles, water bottles. We shredded it, we mixed it with natural rubber. Now PET and natural rubber is something which is not an compatible. It's an incompatible material. We did certain change in the formulations, and we came up with a compatibilized sheet of the material and utilized this material for, like, creating this type of sensors which are self-powered. Okay, you do not need any external power supply for making this, and you can use this for something smart locking system. So this is something, an upcycling strategy that we have done. Not only that, I'm not going to talk much about this because we are still in our developmental phase. we have developed certain rubberized, self-powered material which can recognize, you know, uh, as you can see, different letters, whatever you are typing. Like it's more of an handwriting recognition. If you see, when you write on this self-powered material, whatever we have developed, for the letter A, you get certain signal. If I take I, it is distinctly different. And if I take Z, which is again very distinctly different. So we repeated more than 1,000 times for one user, and like that way we have data set for multiple users. Okay, and we are basically training or creating an artificial intelligence based model wherein you can typically utilize the same for AI based handwriting recognitions using this next generation rubberized self-powered material. Okay, and this is, I'll come to the last slide of mine, wherein this is like, just before the, almost I should say 40 minutes before today's talk, we were working on this and we have the final prototype system wherein we have developed a solution for smart home. Like you can power up your fans, your lights and everything using this type of a self-powered sensor. So this is something, a remote which we generated. You get to see here two switches are there, which is one for the fan and one for the light actually. Okay, this is a kind of a 3D printed box we made for the same, and inside this particular a few electronic elements are there and couple of self-powered sensors are there. Okay, so what you get to see here, you need to switch on the remote at first, and at the far end you see here a tube light is there and a small miniaturized fan. Actually I stole that from my son. So you see, if I press it, you can use it as a kind of a remote, and this is a self-powered rubberized remote we call it, and this is operational even at a distance of 400 meters. Now you can put the fan also on. You can see we attached a piece of paper here so as to show that the fan is working. You can control the speed of the fan as well, and also you can have both controlled together. Both the fan is working, both the light is working, and depending on the utility, the number of utility for the smart home you have, you can increase the number of self-powered sensors here, and you can make a sustainable solution for smart home, and that also utilizing your existing electronics. Those are sitting at your home. You do not need a smart bulb or a smart fan. So this is completely an internet free solution that we can make using this self-powered rubberized sensors. So with that, I conclude my talk. There are certain challenges which are typically also associated with this technology. This technology is something is in a very niche stage. A lot of optimization is still needed. People are working on that. There is a strong demand for bio-based and sustainable nanofillers and bio-based materials, because we have to be very careful. Like as per the United Nations report, there is going to be a tsunami of electronic waste. And now if we see, there is a huge impetus towards buying this, wearable devices and wearable sensors. Left and right, people are buying them, but nobody is talking about how to dispose them effectively. So there is a strong need for making this sensor elements using bio-based materials so that at the end of its lifetime it can degrade by its own. Okay, now there is a strong need, already we have started to utilize machine learning and computational design. We have done a lot of work on the computational part also. Due to the paucity of time, I have not discussed about those things. Maybe in some other occasion I can talk. Okay, so you can have all this integration, and this can be a kind of a take-home message or a future direction in this particular technology what we have been doing. With that, I would like to thank Peram for sincerely for inviting me into this wonderful session which he conducts, and it's pretty interesting talks he arranges. And thank you, Ferrum, for giving me this opportunity. And I'm open to questions if there is any. You can ask me right now, or you can also feel free to drop me an email in either of this email ID. I'm open to collaboration. I'm open to technology transfer, because as you have seen, there are multiple prototypes which we have developed, and this has been tested for multiple times, and I'm open for technology transfer. With that, thank you so much. If there is any question, I'll be happy to answer.
Wow, fantastic. Excellent presentation, Titash. Really good. We can see what's happening in the rubber research world. The smart solutions, smart elastomers. Wonderful. Guys, now as Dr. Titash has mentioned about, if you have any questions, you can ask now, and she will address it. So Titash, already have a couple of questions have been posted. Let me show you on the screen, okay?
Right.
And
Sure.
then we can discuss it. And if you like to ask question directly, I can allow you to open your microphone as well. So just raise your hand, and I will allow your microphone to open. Okay. Let me show the questions on the screen first. Okay, let's invite Karthik Raupati to ask question first. Yeah. Karthik, can you open your microphone? Turn on your microphone, please.
Good evening, Doctor, and good evening, Peram. It was a really fantastic presentation. Very happy to know the kind of work that's going on in IIT. So I just wanted to know, is there any work going on soft robotics?
Yes, we are doing
There's
some.
a lot of,
Yeah,
yeah,
we are
please.
doing something on the soft robotics as well. Smart grippers, we are working. Not only the smart grippers, we are working a bit advanced type of soft robotics. Like for instance, let's say this is a cell and this is a business card. So the grippers that we are utilizing, it can basically perceive what type of material it is picking up. So now you can understand it is not only a smart gripper, but that is also trained appropriately using the AI to have that type of understanding as well, what kind of or how much pressure, how much force it is going to give into the system. And we also have some we have some joint publication with one of my colleagues also, Professor Kingshuk Naskar, very good friend of Peram. So we also worked on some shape memory material, which are like can be electrical heating can be possible, and you get the shape memory behavior for those materials using electrical heating, leveraging this type of technology, whatever we talked about. So these are the
Thank you,
two.
Doctor.
Yeah,
It's really interesting to know. I would love to know more about your work.
yeah.
Maybe I should be visiting you sometime. That
I
would be the best way to know more
looking
about
forward.
these things.
Looking forward. I'm always open to collaboration, because I was also associated with industry, so I have the experience of commercializing products. So that is something I always look forward to commercialize these products, whatever we are making.
All right.
Perfect.
Sure. We'll definitely plan and visit you sometime.
Thank you so
Thank you,
much.
Doctor.
Thank you, Karthik. Let's show you some questions on the screen.
So the question is, what are the key performance traits that makes rubber materials attractive for electronic component, especially when compared to plastics or silicones? Okay. Firstly, rubber brings in the desired flexibility. Okay. Now, one of the major caveat with the plastics is that they are typically sometimes you won't get that kind of flexibility into the system. Okay. Sometimes there are other factors like in plastics. You have the crystallinity effect or the semi-crystallinity effect that we have seen in very fundamental studies, that controlling the conductivity of the system becomes little tricky. Sometimes, if it's a semi-crystalline material, the filler prefers to sit in one of the phases actually. So controlling that conductivity becomes little tricky. Okay. And here you can have a very good stretchability, bendability, conformability to the skin is very important if you are talking about any skin sensitive material. So rubber is having all those benefits. And silicone is also a rubber, because I worked in a silicone industry before joining the academics. So silicone, I'm not sure the person who has asked this question which silicone they are referring, but if you are talking about these silicone rubbers, they are one of the sorted choice for making these wearable devices, because especially the one which are having direct contact with the skin, because it's a biocompatible material. It does not induces any irritation to the skin. And secondly, silicones does have a very good oxygen permeability that helps in having an irritant free material attached to your skin. So silicone is a very good material for this wearable. I'm talking about silicone rubbers, but if it is silicone coating or anything, I don't have much idea. Okay, thank you so much. Next question, please. Are there any specific rubber compounds or formulation that stands out for use in medical instrument, especially in contact with human body? I think I partially addressed this in the previous question. It is basically, you can think of polydimethyl siloxane, which is the silicone rubber, which silicone rubber based materials can be effectively leveraged. Okay, the second thing is natural rubber can also be looked into, because natural rubber is also biocompatible, although it brings in irritation in some cases. But natural rubber is also something which can be very well utilized for this application while in contact with the human body. Okay, next question, please, Param. Is the integration of rubber in e-skin, soft robotics, or stretchable display moving to lab to industry? Yes, it is. There are multiple companies. Actually, I should have shared that. I have a very nice, mapped out who are the companies who are working in this particular domain. I did that homework as well. Now I can name a few. There are companies like Henkel, 3M, okay, and many other. So they have all these particular rubberized sensors or polymer based sensors, which are typically, commercialized. They have products in market, and they work on the rubbers. I'm not sure which rubber they utilize. I have not much. I have an idea, but I cannot talk much about that. But those type of companies are typically bringing it to the industry, or rather, I should say, the market. So, and many other things are going to come soon, because, like I mentioned, especially the energy harvester technology is something which is in a very niche stage. It's a very new kind of a technology which has been developed only, I would say, 12 years before. Okay, so that will take some time for real-time applications. Although we have developed a very nice prototype, if anybody is interested for taking this smart home care solution, please feel to reach out to me. But other sensors are something which are already there, well placed in market. Thank you. Next question. What are the next question is, what are the processing or fabrication challenge when designing rubber component for electronic applications? Now this is something, a kind of a universal challenge that people have dealing with nanomaterials or nanocomposite, because until and unless you have a very good dispersion of the nanomaterial, you know the tricks of dispersing this nanomaterial into, let's say I talk about graphene. Like for instance, I have been working on graphene for the last 15 years. Okay, so I have some knowledge, know how to have a well dispersion of graphene in the rubbers. Okay, but you know, if you know those secrets or recipes how to control the dispersion of these nanomaterials into the rubber matrix uniformly, homogeneously, and there should be very marginal batch to batch variation. Okay, then you can basically have a very good property yielded out from this sensor or the electronic material. Okay, but if you are not able to do so, then mixing is one of the biggest challenge which I think is associated with this particular technology. Okay, Piram, next question, please. The next question is, what advice would you give to students or researchers looking to work on rubber electronics application? Well, uh, if it is students or researcher from India, please come and join me. I am ready to help you out. We do a lot of crazy stuff, as you can see, for the last 1 hour. And jokes apart, but what I would like to say is that it is a very interesting and very demanding, you know, field of work, and students should definitely pursue. I believe it is one of the hottest topic currently in the academics, as well as there are many MNCs who are looking for, you know, solution, technological solution using this rubber electronics material. So I think this is a very interesting field to pursue research work. All the best to the students. Thank you. Yes, in terms of the sensitivity and the durability, sensitivity, these materials can also beat the traditional sensors. Like I can tell you that to the best of my knowledge, I might be wrong, but we have done a thorough exercise. We don't find any traditional sensors which can pick up those, you know, pulse rate. Like let's say that works on the principle of a strain. It's nothing but a strain gauge, the rubberized material which I was talking about this. Okay, I didn't find out any such traditional strain gauge which can pick up your radial artery signals that neatly. Okay, so I can say in terms of the sensitivity, they are pretty good. Okay, and now coming to the durability also. So to be very honest, you know, if you are talking about the metallic sensors or ceramic based sensors, and depending on the applications area where you want to use these sensors, it might not be that good. But one thing I can tell you from my experience, whatever I have garnered for the last 5 years in this domain of the sensor, whatever I have shown, these are like extremely, you know, cost effective. Like it is very much similar to the glucometer strip that you use. Like you can use it for one time and throw it away. Like these are all cost of peanuts actually. If you honestly see the manufacturing cost, if I include the labor charges of making this also, they are not very high. So one can afford to have a, let's say, using it for 10 times and then throwing it away. So that's how I would like to answer this particular question. Yeah, like I mentioned, I would like to request to refer to the you know, some of the companies, or you know, whomsoever at this. The question is, are there any example of successful commercialization of rubber-based components in consumer electronics? Actually, I'm not sure about the consumer electronics, but in automotive industries, there are many. Due to conflict of interest, I cannot name the products which I worked, and those are commercialized. Those are basically for the automotive industries applications. So there are many such electronic component. And also in consumer electronics, if you see, when I say rubber materials, this is one part I have discussed today, that is on the development of the sensors. But there are also a lot of rubber based electronic gels, potting materials, thermal interface materials, which are also there. Like for instance, there are a lot of thermal interface materials which are made out of silicone rubbers and appropriate formulation, and they are very effectively utilized in your mobile phone. So they are very much well in the market. Okay. Next question, please. If there are any. Are there any government or private funding programs in India supporting R&D in the specific areas? The answer is yes. We got a couple of, not we, I should say, one is we and one is I. Firstly, I got a very big funding from Indian Council of Medical Research to conduct, on the healthcare part of this particular rubberized sensors. This is one. And then I would say we got one very big mega project which is sponsored by the Ministry of Electronics and Information Technology, who are funding it and want us to take this material to next level in product scale. And for that also we are looking into commercial partners actually who can help us take that material to the market. I think I have answered most of the questions, and if there are any further questions, please feel to drop me an email. I'll be very happy to answer, and you can just Google out my name and Google will direct you to my page. I hope I was able to give the clarity on this particular topic.
Okay, thank you, Dr. Titash. It's excellent and very interesting and insightful for the people to understand more about the rubber, used in the electronics industry. Yeah? A really good one. So let's wrap up the session. Would you like to give any final message to the audience?
No, the final message is the frame is in today's world. The frame is changing very rapidly. I still remember my father used to use a mobile phone. If you throw it on somebody's head, it's going to break your head apart. And now if you look into the phone, they are becoming so sleek, they are becoming small. So things are changing very fast. And I'm pretty sure that change or the rubber industries are also going to adopt, both in terms of integrating this new type of technology into their existing product line for the future to come. So that's what I would like to say.
Super. Thank you very much, Dr. Titash. Wonderful presentation. I look forward to welcoming you in the future sessions of the TechnoBiz Rubber Tech Talk. Thank you.
Thank you so much. Bye-bye.
Okay, guys, that's the end of the today's TechnoBiz Rubber Tech Talk on rubber materials for electronics application. I see the things happening in this area, very interesting, inspiring, and Dr. Titash has summarized very well on his research developments at the IIT Kharagpur Rubber Technology Center. I do encourage you to connect with Dr. Titash Mondal. He is really, a young and inspiring researcher, and particularly developing interesting solutions for the rubber industry. If you have any projects, please reach out to him. And also, you may think about commercializing some of his innovations as well. Without any further things here, so let's wrap up the session here. Thank you all for joining the session today, and I hope to invite you in the next episode of the TechnoBiz Rubber Tech Talk. Thank you all.